Good afternoon, everyone. Today we are here to present the analysis of the research paper regarding the training very deep networks, and we are group number 2. The members are myself, Shamra, Chamath, Diwanga, and Wishwa. Next slide, please. Okay, so regarding the background details of this research paper done, so the authors are Professor Jurgen, Professor Durgan, Klaus Greff, Rupesh Kumar, all from the University of Lugano in Switzerland, and they published this research paper in the International Conference on Machine Learning, which was held in July 2015, with 600 plus citations. Next slide, please. So what does this research paper try to address? So we know that depth of neural networks are a crucial point at present, and this deep neural networks has played an important role in the breakthroughs in supervised machine learning. So training these deep neural networks has become difficult with the depth increase and is a open problem at present. So as the number of hidden layers increases, the number of inputs in these also increase, and we are so inspired by the LSTM recurrent networks. They have come up with a network which is known as the highway networks, which can be trained by the simple gradient descent, and thus enabling the study of this deep neural networks efficient architecture. Next slide, please. So as the previous group thoroughly explained what the highway networks are and how they came up with this network. So as in simple, it is an opposition. Highway networks are opposed to the traditional plane networks, and the information flow across many layers due to the transform gate and the carry gate, as you can see in the picture. So, next slide, please. And what we try to bring out here in this presentation is the experiment and the analysis carried out in order to make this a success. So while performing the experiments, all the networks were trained using the stochastic gradient descent with the moment. So what stochastic gradient descent does is it computes the exact derivative derivative of the function, and instead they estimate it in small batches, and so exponentially weight averages and provide a better estimation for the actual derivative. The momentum helps in accelerating the gradient, as you can see in the picture, in the right direction to the function. So this method is most popularly used in the optimization algorithms in deep learning neural networks. And also an exponentially decaying learning rate was used with optimization using the data sets, which will be discussed further into the presentation. So all these convolutional highway networks utilize the rectified linear activation function in order to compute the block state edge of the highway networks, and in order to obtain a better estimation of variability classification, the mean and the standard deviation was considered and put it into a equation as shown. And these experiments, they have performed these experiments using the CAFE framework and the brainstorm frame. Next slide, please. So this is how they can optimization. As an example, I will use the MNIS dataset they have used. So in all these networks, networks, they have used the first layer and which is connected to a plane layer, and they are followed by hidden layers, which can be plane or highway network layers. So, and then finally the network output is produced by a softmax layer, softmax layer. The picture in the slides show you the training of the network for the MNIS data. So by performing random searches more than 100 runs in both plane and network layers, they try to get the hyperparameters for the initial learning rate, momentum, learning rate, exponential decay, and in the highway networks, they also consider the initial value for the gate bias. Next slide, please. So this picture shows the comparison of the optimization with the plane networks and the highway networks with various number of layers and depth. So the left side picture shows the training curves for the best hyperparameter settings, and the right side picture shows the mean performance. So the plane networks become much harder to optimize with the increasing depth, while the highway networks with up to 100 layers can still be optimized to to best with the error being really low, error being comparatively low to the plane networks. And it also can be seen that that the highway networks constantly converges faster than the plane ones in the left side picture, if you with the increasing the number of layers. So, and this research is conducted on different data sets, like data sets which are small as well as very large data sets, in order to compare the success of this highway network in different sizes of data sets, and that will be explained to you by Wishwa. Wishwa, over to you.
Thank you, Shamra. Can you hear me? Can you hear me?
Yes, we can hear you.
Thank you, Shamra. In experiment, they done experiment in two ways. In first case, they use MNIS dataset, and here the MNIS dataset has 16,000 training examples and 10,000 test example. They train 10-layer convolution highway network on MNSI dataset. It contains 9 convolution layer and softmax output layer, and they use 16 and 32 filter map in this case. as you can see in this table, there is no big difference in highway networks, because highway networks doesn't perform well in small data. In the second case, they use CIFAR 10 and 100 dataset for experiment, and those dataset look like something like the CIFAR 10 10 dataset has 16,000 color images in 10 classes, and CIFAR 100 dataset has 100 classes contain 600 images per each class. And with comparison to the fitness, max layout network can cope much better with increased depth compared to the traditional activation function. But on CIFAR 10, through paint block propagation only possible for max out networks with a deep up to 5 layers with 250k number of parameters and 30m number of multiplication. So they have found that they can easily train highway network on number of parameters and operation comparable to those of fitness in single stage using sophisticated gradient design, and they have got high accuracy on the test set, as you can see in this table. Comparison to the set of the state-of-the-art method, they perform experiment in more common setting of global construct, normalization, normal translation, and mirroring of image, because their aim is to train the because their aim is to train the hyper network aim is to only because their aim is to only demonstrate the deeper network without losing ease of training and generalization ability. And in here they replace the fully connected layer used in the network in the previous section, and they reuse the hyperparameters in last section also. So as you can see in this table, because of that reusability, there is no big difference here, but they can prove that they can get quite possible better result with better architecture and hyperparameters. So I invite Chamath to continue rest of the thing. Chamath.
Thank you, Wishwa. Now I am going to talk about the analysis of our paper, depending on the visualization of best 50 in layer highway networks. as you can see in this picture, we have done our research on the paper for single random training sample. As the paper indicates, the first row shows the trained on MNIST, and the second row shows trained on CIFAR 100. Here we are going to discuss about the inner workings of these layers. When it comes to the layers, the first hidden layer is a plane layer, which changes the dimensionality of the representation to 50. Then other 49 highway layers, which are represented in y-axis, contains 50 blocks as indicated in the x-axis. And the first column shows, as in the picture, the mean output of the transform gate over the training examples. And the second column, the first column shows the transform gate biases, which initialize from -2 to -4. And the second column depicts the mean output of the transform gate over all training examples. The third and fourth columns showed the output of the transform gates and the block outputs using TANH for a single random training sample. When it comes to the analysis part, the transform gate of the two networks were initialized to -2 to -4 respectively. Can you move to the next slide, please? As we can see in these graphs, the most biases decreases further during training. And as in the second row, the CIFAR 100 network, the biases increase with depth, forming a gradient. And that gradient inversely correlated with the average activity of the transform gates. And that is depicted in the second column. In that case, strong negative biases at low depths are not used to shut down the gates, but to make them selective. When it comes to the overview of these outputs, they stay constant over many layers, forming patterns of strips as in the column 4. When we analyze this, most of the changes in outputs happens in early layers, like layers less than 50 for MNIST and layers below 40 for CIFAR 100. Next slide, please. When it comes to the routing of information, in this case, one possible advantage of the highway architecture we analyzes is that the network can learn to dynamically adjust the routing of information based on current inputs. In the mean transform gate activity, as you see in the second column, and the single example transform gate outputs as indicated in the third column, most transform gates are active on average and show very selective activity for the single example. As this is a data dependent routing mechanism, This implies only a few blocks perform transformation, but different blocks uses different samples. For MNIST digits 0 to 7, substantial differences can be seen within first 15 layers, while CIFAR class numbers 0 and 1, the differences is spread out all the layers. In both, but in both cases, it is clear the mean activity pattern differs between the classes in there. Next, I invite Diwanga to continue with the layer importance.
Thank you, Chamath. When we get in the layer of importance, since we bias all the transform gate towards be close, in the beginning, every layer most copies the activation of the previous layer. In that question arises that the training is going to be change this behavior. For that, we investigate the extent of the which listening single layer affect the total performance of the trained networks in the optimization section. In here, the listening means that we manually setting all the transformation gate to layer into 0, that forcing into the simply copy of its inputs. For each layer, we evaluate the network on the full training set with the gates of that layer closed. In this figure, you can see the resulting performance as a function of listen layer. In x-axis, you can see the number of listen highway layers, and the y-axis shows the mean cross entropy error. The non-least performance is indicated in the dashed line in the bottom. For the MNST, the left figure, we can see the error rises significantly if any of the early layers is removed. But in layers, the 15 to 45 seem to have close no effect the final performance. You can see about 60% of layers don't learn to contribute to the final result, likely because the MN is a simple dataset that doesn't require much depth. On other hand, CIFAR 100 dataset with performance is degrading noticeably when the removing of the first 40 layers. From this, we can say that the complex problem, a highway network can learn to utilize all of its layers, while the simple problems like MNST, it will keep many of the unneeded layers idle. Such behavior is desirable for the deep networks in general, but appears difficult to be obtained using the plain networks. Next slide. Yes, as a sum up, we can say the deep highway network can directly be trained with a simple gradient descent method due to their specific architecture, but this property does not rely on the specific nonlinear transform, which may be complex convolutional to recurrent transform. A possible objection is that the many layers might remain unused if the transformation gates stay closed. So our experiment shows that this possibility does not affect the network adversely. Deep and narrow highway networks can be matched or exceed the accuracy of wide and shallow max-out networks, which would not be possible if layers did not perform useful computation. Additionally, we can exploit the structure of highways to directly evaluate the contribution of each layer. So, for the first time, highway networks allow us to examine how much computational depth is needed for the given problem, which cannot be easily done with the plain networks.